name is Damir Svrtan. I work in the studio engineering organization in Netflix. And Netflix is often referred to as the pioneer of the microservice movement. And being there for the last year and a half, I want to talk about my practical experience after being surrounded by microservices and some of the patterns our team uses to tackle distributed data. But before I get into microservices and stuff like that, I want to talk about a brief history of Netflix. So most of you are probably aware that Netflix existed before being a streaming service. It actually existed for 10 years by shipping DVDs to your home. In red envelopes, you would watch the movies however many times you'd want, and there were no late fees, so you can return it whenever you want as well. And a fun fact is that this business actually still exists and is used by more than 2.5 million people in the US. Now, that was the first phase of Netflix. The second phase, as I mentioned, is the streaming service, which basically changed how people watch content. But it was a risky move back in 2007 for Netflix to become a streaming service because streaming technologies were not really good back then. But eventually, Netflix provided a way for people to watch great content without being disrupted by endless commercials. Now, in 2013, another big shift happened at Netflix, and that was producing original content. What started in the early days with House of Cards, and then continued with Orange is the New Black, Stranger Things, Black Mirror, and so on, now Netflix produces hundreds and hundreds of original shows and movies, way more than most major film studios actually combined. Now, was that a big shift for Netflix? It surely was. All of a sudden, Netflix came from being a technology company where everything is fully automated and performs very efficiently into the entertainment business. Now, the movie-making business is a 100-year-old industry, and in many ways, it hasn't actually changed a lot since it started. Most of the work is still done on paper, and a lot of it requires manual labor. So, does anyone know what this is? Fax machine. Yeah. So, I personally don't have an idea how to use one of these, but every single movie production out there uses fax machines to distribute endless amounts of paperwork. Just to give you a sense of what endless is, there are instances of movie productions that manage to print out more than 50,000 pages within the first week of shooting. At the scale that Netflix is producing content, these traditional means do not work well. Now, the problem space and the number of domains for movie productions and film studios is huge, from deciding which scripts are going to be produced, to deciding what content will be acquired, to searching and discovering talent and actors, to managing contracts and executing payments, to finding shooting locations all around the world, and title localization, subtitles, dubbing, marketing. It's absolutely endless. So how does Netflix tackle these problems? Netflix tackles these by using technology and creating apps that cover key part of every production. Netflix is creating a first fully digital studio to help automate the boilerplate and boring parts that usually creatives do not want to do. We're talking about a suite of more than 50 applications that cover the previously mentioned areas and much more. Now, Netflix actually started tackling the whole studio space with a monolith, with a Rails application. It allowed for rapid development and quick changes while the knowledge of the space was non-existent. There's a ton of apps at Netflix, but this Rails backend is still the largest backend at Netflix Studios, and it's pretty big. At one point, it had more than 30 developers working on it, and it has well over 250 database tables. Now, a lot of these areas, as time passed, started getting specialized apps, and we started decomposing the Rails monolith and migrating data into microservices. And the decision was not geared by any kind of performance issues or anything like that, but with setting boundaries around all of these different areas, as there's a lot of people working on those right now. Now, I joined Netflix about a year and a half ago. And as I've joined, our team started working on a new app that crosses multiple domains of the business. Now, we decided to build this app with Ruby and Rails because we had the expertise with Ruby and Rails. Generally, Rails supports agile development, brings up the team velocity, the time to market is minimal, and the amount of gems is unbelievable. Like, we do not have to build or already solve problems or already build stuff. Now, one of the key elements that describes Rails is its pragmatic use of the active record pattern. And the active record pattern, why is that? Just a second. All right. Now, the active record pattern mixes a lot of things into one class. You got domain objects, you got business rules, you got validation, you got persistence, all in one class. Now, that's great for rapid development. However, that's how we end up with models that are tightly coupled to the database, and decoupling those is a pain. Now, why am I talking about decoupling? Well, what makes working in the Netflix Studio special is that you start dealing with a lot of distributed data. If you need to work on a project that cuts through multiple domains, you start working with various different data sources. These are some of the examples of data sources that we might be working with. It's a polyglot environment, and our users might be, like, we would get our users behind a REST API endpoint, but some movie information might be behind a gRPC endpoint. Some of it might be behind GraphQL. Another API might follow a JSON API specification, and some of it might be in our local database. So once we started this project, we actually knew that one thing we need to tweak in regards to Rails is the persistence layer. Now, we have a key thing to keep in mind while we're building a new app, and that is that data that lives in our database today might live in a service tomorrow. So just to give you a little bit of context, we might actually be the original authors of some set of data or a type of data, but the source of truth for that data might transfer because the whole area might have a broader use. So all of a sudden, we're not talking to a database, we're talking to some gRPC or REST API or something else, some kind of other endpoint. So one of the things we knew while building this app is that we do not want to rely on a protocol. Now, we knew that we needed an architecture that clearly separates the business logic from any kind of implementation details and protocols. What we realized with all of this in mind is that the perfect architecture for us that is solving most of these problems is hexagonal architecture. Now, the idea behind hexagonal architecture is to put inputs and outputs at the edges of our design. What would be the inputs? The inputs, an example of an input would be controllers or requests hitting our application through the controller. And now the outputs would be data flowing into some kind of persistence layer. And by doing that, by isolating the inputs and the outputs, we can isolate the central logic or the core of our application from any kind of outside concerns. And having inputs and outputs at the edges mean we can swap out their adapters without changing the core code. So we can swap out our whole API layer, or we can swap out our whole persistence layer, or just parts of it whenever we need. And no business logic should change. Now, let's talk about a couple of core concepts that we deal with here and that we have built in our app. And these are by no means any new or revolutionary concepts, as most of them you might have actually heard from hexagonal architecture or Uncle Bob's clean architecture. Now, at the heart of our domain, we have our entities. An entity, in our case at Netflix Studios, is a movie, a production, a shooting location, an employee, and so on. And entities by themselves do not know where they're stored. This is unlike what Active Record does. They do not have any kind of knowledge whether they're behind some API endpoint or what kind of database table they're stored to. Then we have our repositories. There are interfaces into getting entities as well as creating and changing them. Methods defined on them usually return a single entity or a list of entities. And they keep a list of methods that we use to communicate with data sources. Now, what would be our data sources? They are our adapters to different storage implementation. A data source might be an adapter to a SQL database, something like Active Record, or an adapter to Elasticsearch, or to a REST API, or even to something much more simpler, just a JSON file or a CSV file, or even a Ruby hash or a Ruby array. And this is usually where the saucy implementation of fetching and pushing data is kept. And then at last, our fourth concept, we have our interactors. There are classes that orchestrate how a certain domain action is performed. They're very similar to what developers usually call use case objects or service objects. And they're classes that are very explicit about what they do. They implement complex business rules and validation logic specific to that domain action. So this is a high-level overview of what those concepts are in theory, but let's see how we actually implemented those concepts and how we design our domain with them. So let's start with entities again. An example of an entity in Netflix Studio domain can be a production, like a physical production. Examples would be a season of Black Mirror or a season of Stranger Things, or a movie production such as The Bird Box. Each of them have an ID, a title, and a logline. And to actually define them, we use the dry struct gem from the dry-RB family of gems. What dry struct enables us is to describe our entities by listing their attributes and setting which of them are required and which of them are optional. And as said, they do not have any kind of persistence knowledge. Those are outside concerns. We need to be able to model our domain without the data source implementation details. Now, for repositories, we actually build a custom DSL, a really small one, like a 50-line DSL, to describe our repositories. We describe which entity they work with and what their default data source is. So you can see a production repository actually works with a production entity class, and we inject a movie production data source into it. And a movie production here can be just an adapter to a REST API or an active record model. And as said, they keep a list of methods that we use to communicate with data sources, and they wrap those data source results into entities, into the entity that we defined. And you can see, as said, that we inject the data sources into them. Why is that? Well, actually, we want to be able to swap those data sources when needed. The only thing those data sources need to conform is to the same interface. Now, what would be our implementation of a data source? Well, if we're talking directly to our SQL database, our data source will be just an active record model. It's where any kind of SQL logic, such as selects, groupings, aggregates, or anything like that, will actually be kept. And those implementation details are kept explicitly there and should not leak further into our business logic. Now, if we're talking to, let's say, some REST API, we'll need to create a class that will fetch data using some kind of REST API client. Now, you can see that both of these classes actually have the same interface. So they both define the same method. Now, why is that? Well, that makes our repositories independent of what our data storage system is. We can have a default one and easily use a different one if we need to swap it at any given moment. The changing a data source, as said, does not whatsoever have an impact on our business logic, and that is great. And another great thing about doing it this way is that it's a one-line change. So in production, we can easily flip it, and if we realize it's not working out on an initial deploy or something like that, it's also very easy to roll back. We do not need to do a ton of changes. And finally, let's talk about how we implemented interactors. So for building interactors, we use the interactor gem. The interactor gem is great as it provides a uniform way of stating whether an action is a success or a failure. Now, we also built a really small DSL on top of that enables us to define what the arguments and what the dependencies of the interactor is explicitly. So a domain action could be to onboard a production into our system. And what we define on it is that it should receive a production ID and a vertical ID, like what content vertical it is. But this is too much getting into the domain. But design like this makes our logic totally decoupled from the persistence layer, because if you look very closely, we also define what the repository we deal with is defined in the call method. Now, why is that? Well, if we leverage dependency injection, we can actually properly unit test our interactors, which I will talk a bit about later on. Now, one thing I want to mention is, although Rails does not aim at separating business logic and persistence like this, like we have done here, if you're interested more in this topic, in building apps in a clean architecture fashion or hexagonal architecture, please do check out the Hanami framework. It's a great framework that follows the principles of clean architecture, and all of the terminology that I've mentioned here is implemented in the Hanami framework. One of the reasons why we didn't use it back when we started our application is because we wanted to leverage the large ecosystem of gems supported by Active Record, stuff like access lists, counterculture, and various numerous others. And that enabled us to move fast and ship new features on a regular basis. But if we were starting this project now, a year and a half later, we would highly consider Hanami. Now, we have touched the data sources part a little bit, but let's talk more about implementing those data sources that actually depend on external services like REST APIs or gRPCs. Now, as we consume data from different APIs, we need to have a lot of API clients. And there are two main approaches to solving this problem. The first one is we could handwrite our API clients and package them up into gems. However, that takes a lot of time to write. They're usually error prone, they easily get out of date, and you always have to add new features by hand. And generally, the maintenance burden is too heavy, and it simply does not scale for us with just the amount of APIs that we need to communicate with. What we rather opted in is for auto-generated API clients. It's basically any API that we work with has to be able to provide a very easy way to interact with it, either by following a specification or having documentation from which we can generate a client. And we usually generally talk to three different types of APIs. One are REST API, gRPCs, and JSON, and APIs that follow the JSON API spec. And for each of them, we found easy solutions to move fast. Now for REST APIs, we usually have at Netflix Swagger documentation. So what we use then is Swagger code generators that take that documentation and generate clients. And we usually package up those clients into gems and publish to our own gem repository. And with gRPC, it's kind of in some way similar. We just get protobuf files and we generate clients easily from there. So we don't have to put a lot of effort into maintaining those. And then with the JSON API specification, which prescribes a very uniform way how to expose resources and receive requests, thanks to that fact, it's very actually easy to use JSON API generic clients to fetch various resources. It's really minimal work. Now, if you go down this route and you need to communicate with other different APIs as part of like the backbone of your application, you'll run into some complications. And one of the things you will have to do is shift a bit of your mindset with the fact that you'll have to deal with errors, with like those microservice errors or network errors, and it's a big shift. So if one thing is for sure, is that the network is unreliable. When your only data source is a database, rarely anyone adds extra code for cases when a database is not reachable. As if you have a single database, if there's a database outage, your whole app is down. Like you cannot do much probably. But this kind of happy path thinking does not work well in a microservice environment. Microservices will fail and there will be outages, even if you work at Netflix. And one thing we need to be prepared for is graceful failure. So what is the experience if a downstream service fails and has a total outage? We need to be sure that an outage of one microservice does not take our whole application down, and we need to be able to serve partial data and give clear error messages to our users. Now, one of the things that really helps in a microservice environment and is essential is to be able to properly troubleshoot errors. Now, if a 500 error occurs on a downstream service and you're not sure why that happened, usually without proper logging, troubleshooting can get pretty hard. Now, Another extremely important aspect is measuring, as without that you won't be able to discover what your pain points in your applications are. A good way to solve a lot of these problems is having metrics in place, even simple ones such as what is the success to failure ratio when we communicate with a microservice, or what are this downstream service response times and latency. And even simple things like that can help you a lot. And of course, we need to have some kind of error reporting system, just as most Rails apps do, like Sentry or Bugsnag or Airbreak or something similar. And one thing we need to be cautious about is that we do not overload ourselves with unactionable errors. So we should only report errors that are actually actionable from our side. Let's say if a downstream service responds with a validation error, our team does not have to be alerted about that. That's the thing we need to be sure to propagate to the user and give clear error messages like that. If we bring up any kind of error that happens in our application, what will happen is alarm fatigue to our team. Now, how many of you have heard the phrase alarm fatigue? All right. So, give you an example of outside of tech, and where actually this phrase was coined. If you enter an emergency room in a hospital, probably the first thing you'll hear is a bunch of alarms constantly going off from systems monitoring vital signs on patients, such as the heart rate, the pulse, oxygen, and so on. And a lot of these alarms are actually unnecessary, and as they are unnecessary, medical staff just starts to ignore them. And this was actually a huge problem in the US, because between 2005 and 2008, there were over 550 deaths just due to alarm fatigue, because people would ignore alarms, and when there was actually an alarm that they needed to action on, they would just keep ignoring it. Now, we're not dealing with deaths here, most of us at least, so that's good. But we need to be sure that our teams do not get alarm fatigue. At the beginning, we used to report every single thing, even if it was not actionable. But as time passed by, we removed a lot of those reports, and we set up threshold alerts on our metric system to notify us when a certain amount of calls start to fail. An example would be if 20% of calls start failing to a particular microservice, then alert the team. Then we're probably not integrating anymore well, and we need to collaborate with the downstream service team to work on a fix. Now, a lot of you might be wondering at this point, like, why would we go straight to the data source? Like, why would we ping other REST APIs and so on? And a question you might be asking is whether this actually scales. Isn't it slow to make additional network calls to other services? Well, before I answer that question, let's talk about what would be an alternative design to this. Now, we could, of course, actually keep copies of that data that we need from other services closer to us in some kind of database, like the database that we use for the rest of the development. And we could listen to events whenever that data changes and refresh our copies. So we could leverage eventual consistency, as that is actually the way to go and reach true scalability. But at the same time, it's a solid amount of work. There's always actual questions about whether you want to trade consistency for availability, and in most cases, actually availability wins. If you look at the case of Amazon's shopping cart, availability is the absolute winner. People must always be able to shop. If Amazon, by accident, sells an item that is no longer in stock, there's not much of a problem. They can always give refunds and offer some kind of coupons, and everybody will be happy, and it's perfectly okay. But we're also in two very different positions. Amazon has huge volumes of data and enormous traffic, while our apps at Netflix Studios have the most a couple of thousand users that use them. And at the same time, those users that actually use our apps make big decisions about how our business works and how our production works. So when we show them data, it better be right. It's actually better for us to not show them data than to show them wrong data. So that's why we opt in for being completely consistent. Now, in Netflix Studios, and of course in whole Netflix services must be reliable. They must be highly available, and they must respond in a timely manner. If we encounter a service that is slow, we give feedback to that team, and they're supposed to fix it. And we rely on our services being available, and so far it has been great. If there's actually a possibility for us to avoid synchronizing data in our apps, that is actually the preferred way for us to go. Not, of course, every app in Netflix Studios follows this model. Some of them work with eventual consistency, so some of them sync data and through events refresh their copies. But they also have much more of a specialized use case than our app has, and they don't have such a huge variety of data. We talk to more than 40 different endpoints on different services, and syncing that data would be like a ton of work. Now, what if this in the future actually becomes slow? Like if in the future we, by any chance, I don't know, start dealing with huge amounts of data or need to additionally decorate that data, we will actually probably decide to keep decorated copies of the data closer to us. But that's another reason why this architecture is great, is because it enables us to delay decisions. We're not only in a great position when we need to swap a data source from, let's say, a REST API to GraphQL or something, but we are also in a great position to delay decisions about how we want to store data internally or whether we want to store it or not. So some of the data that we might be fetching from a REST API, we might figure out that this is not working anymore for us, and we can just swap out an adapter and point it to our database, and we will have no changes in our business logic. And that's how we want to do it. Now, there's a thing called a project paradox, and that is that we're actually making the biggest decisions on our projects when the knowledge of the domain that we're building is at the absolute lowest. So just imagine, at the beginning, when you're building a project, you decide what kind of database you're going to use. Is it a SQL database, no SQL database, what kind of SQL database, blah, blah. Like what kind of pub/sub mechanism are we going to use? What kind of search mechanism are we going to use? And so on. And at that point, like during the life cycle of the project, that is when our knowledge is at the lowest. But as time progresses, we know more and more and more, but the scope of the decisions that we can make is lower and lower because we've constrained ourselves with the decisions that we made at the beginning of the project when we didn't have any knowledge. So Uncle Bob said a great thing. The purpose of a good architecture is to delay decisions. Why? Because when we delay a decision, we have more information when it comes time to make it. And that's absolutely true. Now, we currently store some of our data in Postgres, but tomorrow, if we realize that that's not working for us anymore, if we need to switch, let's say, to Cassandra, some kind of NoSQL database, no problem. We can do it. We're not tightly coupled to Postgres. Or if we need a key value store or we need other search capabilities, it's very easy to plug this in and switch. And because we have architected it this way, it's very easy for us to delay decisions. And we can have a polyglot approach where we opt in to have some of the data stored in one kind of database and then some of the data stored in another kind. And that really fits our needs. Now, before I end, I want to talk shortly about our testing strategy and what we did here. Now, we firmly believe that the test suite must be reliable and fast. It's not a nice to have, it's a must. No one wants to run their specs only on the CI server. Like stories of developers running their 30-minute specs suits in parallel on 8 cores only on the CI is not usually efficient. And probably nobody's happy with that. Now, we want to have super fast tests so we can have good development velocity. Now, usually a pattern to test Rails apps is hitting the database a lot. Not, of course, every code base or every Rails code base does it like that, but most of the apps that I've seen constantly hit the database. Now, that's what actually makes it a lot of times slow. Now, for us, when we're testing our business logic, we don't want our tests to depend on various data source implementations, so we test our business logic independently. And what we leverage here is what I've mentioned is dependency injection to easily test our interactors where our business logic is. And with dependency injection, we can leverage verified doubles and decouple our core code from the persistence layer. I'll show you how we did it. Now, we can take an example of, and I'm sorry if not everybody can see this clearly. If we take an example of the interactor that I showed you about onboarding productions, it takes 3 arguments, a production ID, a vertical ID, and a repository. We can just generate production IDs and vertical IDs to be something random because we're not actually hitting the database. And what we do is actually, if we, let's say, want to simulate a failure scenario where like we cannot onboard a production if the production is already onboarded, what we do is create a verified double of that repository, answer any kind of messages or any kind of methods that that repository would get called on and injected into the interactor. And that way we can insert, okay, if through the repository we manage to find a production with the same ID, the response should be failure. And with that we can continue on creating success stories as well and test it in more detail. And with nicely separated interfaces like this, it gives us assurance that this works, and it also gives us super fast tests as this runs extremely fast. Now, besides having unit tests, of course, we have integration specs. But our integration specs are written at 2 different layers. So the first layer of integration specs works on the data sources to check if we are integrating properly with different services. And the second layer of our integration specs are basically end-to-end specs that go through the whole stack. So that go through the request that hits the controller, that calls the service, that calls the repository, that calls the data source, that goes to another service and gets the call back. And now, if we actually make a call to an external service, we record that usually with VCR, so our test suite does not have to make the ping every time we test. And we usually build them in a way where we test one happy path and one sad path while unit tests cover the rest. And now what this produces is a fast and reliable spec suite. I took these numbers yesterday on our test suite, and so within 1 minute and 42 seconds, we managed to run a little bit less than 3,000 examples. And it's lovely to work with a test suite that can easily be run on any development machine without disruption to anybody's daily work. And fortunately, we saw that there are places where we can actually optimize this more, so hopefully we will be able to do that. Now, in conclusion, what I want you to take from this presentation is separating business logic from implementation details really made a ton of sense to us. And it doesn't have to be only that if you're working in a microservice environment. This is generally good practice. So hexagonal architecture really proved to be a great way for approaching problems to us. It generally forces us to think in terms of decoupling layers, which is just what we needed. And if you take one thing away from this, is please let delaying decisions be that. Making most of the decisions at the beginning of a project does not make sense. The decisions actually we made so far for now has made sense for us and have enabled us to move fast. But the best part of this architecture is that it keeps us flexible for future requirements to come. Thank you everybody for listening. My name is Damir Svrtan, and I hope you got a general idea of this topic. This only scratches the surface, so if you want to talk more, I'm happy to answer questions. Thank you.